In the last video on exponential functions, we saw that functions of the form y is equal to some number to the x, say y is equal to 3x was what we used in the last video. We saw that these grow very, very, very quickly. So the shape of the graph that we got in the last video looks something like this. It looked something like this. Gets very close to 0, slowly approaches away from 0, and then bam, starts to explode. And this, of course, is when x is equal to 0. So the y-intercept there is y is equal to 1. But the important thing is it just grows super fast. But this was the case where the base in the exponential function is greater than 1. Here it's 3. If it's 2, it'll still grow quickly. If it was 10, it would grow even faster. What I want to talk a little bit about in this video, and really just introduce you to the idea, is the notion of an exponential decay function. So this is an exponential growth function. An exponential decay function has essentially as its base a number less than 1. So an example of an exponential decay function would be y is equal to 1/3 to the x power. This would be exponential decay. And notice, another way I could write this, 1/3 is the same thing as 3 to the negative 1. So it's 3 to the negative 1 to the x power. I could also write this as 3 to the negative x power. This and this are equivalent. And that's another interesting way to think about exponential decay functions. It could either be kind of a standard positive exponent with a base that's less than 1, or you could have a base larger than 1, but you're going to have a negative x as the exponent. But let's plot this just to get the general shape. And the shape will always be consistent. I'm going to do it for 1/3, but it's going to have a similar shape for 1/2, or for 1/10, or for 1/100th. It'll just be scaled up or down. So let's plot a few. So let's have some x values, and let's have some y values. So let's start with some small values. So let's say that x is equal to negative 3. Well, what is 1/3 to the negative 3 power? That's the same 1/3 to the negative 3. That's the same thing as 3 to the third power, which is equal to 81. Let's do another point. What about negative 2? 1/3 to the negative 2 power is the same thing as it's equal to 1 over 1/3 squared, which is the same thing as 3 squared. You just take the inverse of the number, get rid of the negative, and that is equal to 9. Oh, I got this one wrong up here. 3 cubed isn't 81. That's 3 to the fourth. 3 times 3 times 3 is 27. 27. My brain is malfunctioning. What about when x is equal to negative 1? Then you have 1/3 to the negative 1 power. 1/3 to the negative 1, which is just 3. What about when x is equal to 0? When x is equal to 0, remember, anything to the 0th power is 1. And then let's go to a couple of larger numbers. When x is equal to 1, what is y? 1/3 to the 1 power is 1/3. Let's do one more. When x is equal to 2, we have 1/3 squared, which is 1/9. So let's plot this exponential decay function right here. I want to draw it reasonably neatly. And all of these values, once again, are positive because our base was positive. So it looks like that. We'll start. So let me go. So let's say that this is 10, 20, 30. And let's start at negative 3, negative 2, negative 1, 0, 1, 2. So when x was negative 3, y was 27. When x was negative 3, y was 27. It's right about there. When x was negative 2, y was 9, which is right about there. When x is negative 1, y is 3, right about there. X is 0, y is 1. X is 1, y is 1/3. And so we decline like this. We decline. Let me draw it a little bit neater than that. The decay functions are harder for me to draw. Well, let me do it one more. Maybe I'll draw it this way. Draw it in reverse order. No, that's even worse. One more shot. I think you get the general idea. That's my best shot right there. So you see, a decay function is kind of reversed around the y-axis. We start from a large quantity and we decay very, very, very quickly. So in either case, exponential functions, whether we have exponential growth or exponential decay, let me make sure that you understand this growth applies to this thing up here. This is exponential decay. That either way, when in exponential functions, things happen quickly. Now, using what we know about exponential decay functions, let's do actual word problem. So let me read it here. It says, a person is infected by a bacterial infection. Bacterial infection. And they say when he goes to the doctor, the population of bacteria is 2 million. So at the start, he's got 2 million little critters. 2 million bacteria. 2 million bacteria. The doctor prescribes an antibiotic, which kills bacteria, that reduces the bacteria to 1/4 of its population each day, or that reduces the bacteria population to 1/4 of its size each day. So we have the antibiotic, and it cuts down the population. So it cuts down, I guess we could say reduces population to 1/4 of I guess you could say the previous population. Previous population each day. So they ask us a couple of things. Draw the graph of the size of the bacteria population against time in days. So let's draw this. So day and then population. Population. So let's say on day 0, before you went to the doctor, your population is going to be 2 million. Now on day 1, what happens? On day 1, you've taken their antibiotic, right? The antibiotic is starting right there. So it reduces it to 1/4 of your previous population. So now your population is going to be 1/4 times 2 million, which is equal to what? 500, equal to 500,000. Then on day 2, what happens? On day 2, it's going to be 1/4 of this. It's going to be 1/4 of your previous day. 1/4 of 1/4 of of that 2 million. Of that 2 million. So it's 1/4 of this 500,000, which is 125,000. And I think you're starting to see the pattern that's emerging. On day 3, what's it going to be? It's going to be 1/4 times this thing. So it's going to be 1/4 times this 1/4 times 1/4 times 1/4 times 2 million, which is essentially 125,000 divided by 4. But the important thing is I want you to see this pattern. In general, the population at day n, let me write this in a new color. The population on day n is going to be equal to what? It's going to be equal to 1/4 to the n power, right? This is day n. On the third day, it was 1/4 to the third power times 2 million. On day 2 is 1/4 to the second power. On day 1 is 1/4 to the first power. On day 0, there was actually 1/4 to the 0th power, right? That's 1. So it's 1/4 to the nth power times our starting population times 2 million. Times 2 million. And if we were to graph it, using at least just the points that we have here, we're only going to be dealing with positive x's. So on day 0, we start at 2 million. So let's say this is in millions. So on day 0, we're at 2 million. On day 1, we're at 1/4 of that. So let's say that's 1 million. So then that is 500,000. On day 2, we're 1/4 of this. So this is 250,000. That's 125,000. And then on day 3, we're 1/4 of that. So you see the population of our bacteria really goes down very quickly. Never gets quite to 0. We're always going to have some bacteria. Well, eventually you're going to have one bacteria and you're going to get the antibiotic and it's going to have a 1/4 chance of hitting it. So maybe eventually you'll get to 0. But it slowly gets to 0. But the absolute number decreases very, very fast. Now, they also ask us find the size of the bacteria population 10 days after the drug was first taken. So after 10 days. So that's just n is equal to 10. So it's going to be equal to 1/4 to the 10th power times 2 million. And let's take our calculator out to calculate this. So let's take 1 divided by 4 to the 10th power. To the 10th power, that's equal to this very small number, times 2 million. 1, 2, 3, 1, 2, 3 is equal to, we're only going to have 1.9 bacteria after the 10th day. So we're going to have, this is going to be equal to 1.9 bacteria. So pretty much most of the bacteria is gone after the 10th or by the 10th day.